In this session, I would like to discuss the Cauchy-Euler equation, or sometimes it is Euler-Cauchy equation, and or simply the Euler's equation. It's a variable coefficient linear differential equation. So it's a variable coefficient linear differential equation. So its form is going to be a bit special one in the variable coefficient. So for example, an nth order is a n x raised to the power n and y nth derivative plus a constant coefficient a n minus 1 times the variable part of the coefficient is x raised to the power n minus 1, and there is n minus first derivative, and it goes on to see its coefficient to a to x squared y double prime plus a1 x y prime plus a naught and y, and equal to some function of x. So this is linear and its variable coefficient. However, the coefficients have x raised to the power uh, an integer, and the same order of derivative appears in y. So a simple one of second order, if we consider, so that is going to be a to x squared y double prime plus a1 x y prime plus a naught y, and it is equal to f of x. It has been known that a substitution um, x equal to e raised to the power t can convert this equation to a constant coefficient linear differential equation. And since this topic of Cauchy-Euler equation comes later in the context of linear differential equations, so it is expected that the students know about how to solve the higher order differential equations. They can recognize its um, homogeneous solution and its particular integral. So to proceed further, let's simplify the constants. So I choose a x squared y double prime plus b x y prime, and let's prefer the capital constants a b x y prime plus c y, and it is equal to f of x. So let's develop with our suggested um, substitution. So from this one, I can define dx dt. So it is equal to e raised to the power t, so which is x. And I would like to define from here dy dx. So from chain rule, it will be dy dt and dt dx. So which means dy dx can be replaced by dt dx will be the reciprocal 1 over x and dy dt. So first derivative has been simplified to dy dt structure. Okay. So further, the second derivative d2y dx squared, well, this was the form for y prime and this was for y double prime. So this is going to be d over dx, or 1 over x dy dt. So it requires the product rule to be implemented. So 1 over x and d dx of dy dt, and plus the second function to be constant, and the derivative of 1 over x will be minus 1 over x squared. So this needs a simplification, 1 over x. So this part this can be simplified as d over dx dt, and then d over dx. Oh, no, this one. It is going to be dt over dx and d over dt of dy dt. So, well, this nicely makes up the chain. So we have this one on the chain. Okay, fine. And then it is minus 1 over x squared dy dt. So dt over dx, it is 1 over x. So therefore, it will be simplified to 1 over x squared. Now it becomes d2y dt squared minus 1 over x squared dy dt. So an equivalent of y double prime. So the equation becomes a times x squared, and the equivalent of second derivative d2y dt squared minus 1 over x squared dy dt plus bx, and then it is 1 over x dy dt. This is the equivalent of y prime plus cy, and it is equal to f of x. So this can be simplified. X squared will be cancelled in the first expressions. So this is fine, and x will be cancelled from the second expression. So we have a nice form. So here a d2y dt squared, and these will be collected, and it will form b minus a dy dt plus c times y, and it is equal to f of x, or well, we have the form with the substitution x equal to e raised to the power t. So it is uh, preferable to write this one over here as f of e raised to the power t. Okay, so this has now become a constant coefficient differential equation. So we have the coefficient of second derivative, first derivative, and the variable, the dependent variable y with coefficients as constants. So the form has become similar like the constant coefficient equation ay double prime plus by prime plus cy equal to, say, f of x, so we know we can develop the auxiliary equation. And for the auxiliary equation, we can find the roots. So roots are minus b. So m equals minus b plus minus b squared minus 4ac over 2a. So in our case, we have got a value equal to capital A, where b value is equal to b minus a, and small c is equal to capital C. So the auxiliary equation is going to have two roots, and the solution. For the solutions, we have cases. So by the way, these are for the homogeneous part. So we will look for the m values. So if m1 is not equal to m2, and we have the distinct values, so the homogeneous solution of y, in our case, it will be written here for t. So it will be c1, a constant, e raised to the power m1 times t, plus c2, e raised to the power m2 t. So this is interesting. If we recognize from here that e raised to the power t was our substitution. So I can write, okay, in this step, e raised to the power t raised to the power m1 plus c2 e raised to the power t raised to the power m. So we found here a very interesting thing, that it is x raised to the power m1 plus c2 x raised to the power m2. So this is very, very interesting thing, and that's going to be our recipe while attempting the higher order differential equation of Cauchy-Euler type, that we can start with the test solution as x raised to the power m and start developing the auxiliary equation. So for example, like our case was a no our case was a x squared y double prime plus bx y prime plus cy equal to f of x. So in order to write the complete solution y as a function of x, there is going to be a homogeneous part and there is going to be a particular integral. So for homogeneous part, we will consider that there is going to be a solution which is proportional to x raised to the power m. So with this one, y prime will be equal to m x raised to the power m minus 1, and y double prime becomes m times m minus 1 times x raised to the power m minus 2. With this substitution to equation, so we will get a x squared m times m minus 1 x raised to the power m minus 2 plus b x m times x raised to the power m minus 1 and plus c x raised to the power m. And for homogeneous solution, we have to set f of x equal to 0 towards to the right hand side. So if we simplify all the terms, have x raised to the power m, so we can divide the equation by assuming that x raised to the power m is not equal to 0. So the equation becomes a times m plus b minus a times, okay, a m squared b minus a m plus c, and it is equal to 0. So, from here we have got the auxiliary equation, and now we can develop the roots of m. So m is equal to minus b minus a plus minus, yes, it's b minus a squared minus 4 times a, which is a, and c is c, and divided by 2a. So with the distinct values, like I mentioned earlier, that with the real values, we can write the direct solution as for the homogeneous part, like case 1, m1 is not equal to m2, so we can write the direct solution x raised to the power m, like we started, that it was c1 e raised to the power m1 t and c2 m2 times t. So we can build on it. So case 2, if we have the m1 and m2 forming the complex conjugates, like their forms are alpha plus minus iota b, that is due to the discriminator appearing in the root of auxiliary equation. So our solution, homogeneous solution, will be c1 e raised to the power alpha plus minus, okay, with c1 alpha plus iota beta, and c2 e raised to the power alpha minus iota beta times t, okay, t, or directly, or with the substitution, we can simplify it to x raised to the power alpha plus iota beta plus c2 e raised to the power alpha minus iota beta. So then we can further simplify uh, that x raised to the power alpha can be taken out, and x raised to the power iota beta plus c2 e raised to the power c2 x raised to the power minus iota beta. This form can be simplified. For example, if I assume that z equal to x raised to the power iota beta, so then log of z will be equal to iota beta and times log of x, and this can be further simplified as e raised to the power log of c, and here it becomes e raised to the power iota beta log of x, and here it again converted to z, and this will be then simplified to Euler's identity, cos of beta log of x plus iota sine beta log of x. So with this simplification, we can then write our solution. Y of h is equal to x raised to the power alpha. So C1 uh, cos of beta log of x plus iota sine of beta log of x, and plus similar terms with C2 cos of beta log of x minus iota sine of beta log of x. And then there is going to be another parenthesis. So we can write x of alpha. The parts of cos of beta, they will be connected, c1 plus c2. So this will be connected to another constant, for example, c3. So cos of beta log of x. And we can connect c1 iota and c2 minus iota as coefficients of sine to another constant c4 sine of beta log of x. So the third case where we have the discriminator equal to 0 and m turn out to be just a single value, like in our case it is b minus a over 2a. So this case, if we consider the y homogeneous part as a function of t, so we can write c1 e raised to the power mt. And since we have only one solution, so we know we can write c2 times t e raised to the power mt. And in x, with our substitution, it becomes x raised to the power m plus c2, where with our substitution, x equals e raised to the power t. So we can write log of x equal to t. So the solution becomes log of x times x raised to the power m. So that's how we write the homogeneous solutions of Euler-Cauchy equation. And then for the particular integral, we can use the method of variation of parameters. So that's the recipe for solving Euler-Cauchy equations. So method of variation of parameters for YP development. So let's stop at this point.